Hi everyone, and welcome to the Micro-Learn program from the Global Parkinson Genetic Program and the Aligned Science Across Parkinson's. My name is Lucas Faria, and I'm a PhD student at Universidade Federal de Minas Gerais, Brazil. Today, we're talking about power calculation, an important concept to keep in mind when conducting genetic analysis. We'll divide this video into hypothesis tests, error types, power, and tools. When we're talking about decisions based on statistical evidence, we're referring to hypothesis testing. In a classical hypothesis test, we would typically want to determine whether two identical variables from two different groups are the same, different, one smaller than the other, and so on. Let's see an example of hypothesis testing. H0 is the null hypothesis. Under H0, we assume that there is no statistical difference between the values of the two groups being compared. The alternative hypothesis, H1 or H8, asserts that there are statistical difference between the observed values. We can organize the possible combination of the hypothesis tests in a table like this. We say that reject H0 when H0 is true leads to a type 1 error or false positive, typically denoted by alpha. Conversely, not reject H0 when H0 is false results in a type 2 error or false negative, denoted by beta. The event do not reject H0 given that H0 is true is a complementary event of reject H0 given that H0 is true. This means it's equal to 1 minus alpha. Similarly, reject H0 given that H0 is false is denoted by 1 minus beta. If beta represents the probability of the false negative and you want to ensure the correct rejection, 1 minus beta is what 2's power is the probability of correctly reject H0. So, under the hypothesis we mentioned previously, if you determine a power of 80%, typically the minimum requirement for a test, we're saying you have an 80% chance of detecting a difference between the two variables if it exists. And complementary, there is a 20% chance of erroneous accepting something false, beta, false negative. So, what the factor influence power? What leads to increase or decrease? We can summarize the variables that influence powers into some topics: alpha, effect size, and sample size. Alpha is predetermined before the test, typically set as 5% or 1%. A 5% significance level implied a 5% chance of erroneous reject something true. Effect size. It represents a strength of the relationship between the two variables in a population. This can be assessed through previous research. If it doesn't exist, you can determine a meaningful value for your test. Sample size can increase your power. The more individuals you include, the greater the power. But what is the minimum required? Here we can reframe the question. If we define a value of alpha, beta, and effect size, we can comprehend and estimate the minimum number of the individuals we will require. If there is a large variation in effects we are testing across individuals, this will also impact the required sample size, so you have to consider this factor as well. Some tools can help you understand sample size, such as the developed by Christopher Magnusson. Here, you can specify your input parameters such as alpha, beta, and effect size. Your sample size can increase significantly if your alpha is very stringent or your effect size is too small. If you need something that can be automated and included in your pipeline, you can use packages within R such as ptableR. For a quick installation in user-friendly environment, you can have the option of cheap-hour software. In association studies, not only do alpha, total sample size, and effect size affect the result of our analysis. Other factors such as the frequency of the candidate allele, the proportion of the risk genotypes in the population, and the balance between cases and controls have a direct impact. To assist with this, tools like GAS Power Calculator by Jennifer Lee Johnson are available online. With a user-friendly interface, you can adjust variables that will significantly affect your power. In addition, the tool provides a comprehensive tutorial with exercises that explain what each input component means and the meaning of the conclusion. To prevent wasting resources such as time, money, and ensure patient safety while striving for good outcomes, we need to conduct precise statistical tests. Anticipate errors before you conduct the experiment is essential. Estimate the power of your experiment based on your sample size can help save time and resources. There are numerous tools you can use to estimate your parameters. Do not hesitate to use them. Thank you for listening, and I hope you enjoyed the video. Bye!